shows that it is a form of with a lot of references all over that.
I'm not sure I should have somebody.
Hello. Okay.
Yes.
It's all the audited stuff. When? It's like
Okay. Yeah, sure.
First, I was like, is it actually a chair? Then I saw the picture, but it's like so mistaken. It's like kid fault.
Okay.
I was using it, but I was like,
Okay, so next we have Lisa Lee, who is a new incoming assistant professor in electrical engineering in University of Michigan, and she came out of John Doyle's lab, and as he describes her, is like she is like one of the two best grad students he has ever seen. And then that's what he said. And then she can code and talk at the same time. That's what he said. Anyway, so she's great. And I met her like at the Telluride neuromorphic computing, and she gave like a great talk. And she has actually solved one of these big problems of control theory. And then one of the problems was basically like control is not strictly scalable. And she was able to scale up control in ways that, because it was supposed to be a long unsolved problem, is above my pay grade. I barely understand what she does. But she has solved this long-standing problem of scaling up control to really large systems, which is basically not obvious how you can achieve it. So without further ado, I'll let Lisa tell you about a slightly more biological kind of inspired feedback control. Okay.
all right. Thanks, Gerald, for that introduction, and for organizing and inviting everyone here, including me. So I'm going to be talking about optimal feedback control in sensory motor systems. I assume everyone here is relatively familiar with neuroscience, so I'm going to spend a fair bit of time talking about the optimal control half. Now, as I was making this talk, I kept veering between these two extremes that I've made everything too simple and this is not going to be interesting, and then I've made it too complex and I'm going to lose everyone in the first 5 minutes. So that is to say, if you have any questions, even starting from the first or second slides, please interrupt me right away so I don't lose you in the beginning. Okay, so when I say to people I'm a control theorist, which I am, one of the first questions I'll get is, well, what is control theory? So this is the way I see control theory. It's kind of the language of block diagrams. So I have a nice block diagram here. So on the bottom, we have a dynamical system. Control theorists call it a plant, but this is very confusing if you get near actual plant biologists. So I call it a system. And this system is typically described by ODEs. It has some noise, it has some uncertainty. So it's like, an airplane or a car, right? They obey some laws of aerodynamics and physics. For the control theorists, once you have this system, our question is, how do we make the system do what we want? Now that's very vague, right? So when I say optimal control, what I mean is we'll specify some objectives or some cost function that we want to minimize, and we'll have some constraints either for safety or for like practicality reasons. And you can put that into the toolbox of convex optimization to find an optimal controller. So the optimal way to make your system do what it wants. So what we do is we basically add a feedback controller. So that's the top box there. So you have your system, maybe it's like an airplane. You obviously have some ways of sensing the different states of your airplane. And then you can also influence your airplane by controlling, for example, the jets or the angle of the little ailerons. And that makes a closed loop system. And the controller's job is basically, given your sensory information, what's the best thing that you can do? And control theory is about both designing the controller and analyzing it, and also analyzing the full closed loop. So the system in closed loop with the controller. Now, very much earlier on, there was another branch that was open loop control. And that one is basically saying, well, we have our model and we know what we need to do, and we don't need to sense anything. There's obvious problems with this, which is that if there's anything off with your model, if there's any kind of noise and uncertainty, you're not going to have a good time. So typically these days, when we say control, we mean closed loop control. So I have some examples here of feedback control. I've talked about the airplane. One very popular application right now is robotics. So for example, if you have a robotic arm, you have the equations of motion for it. Basically, it's a lot of trig. And then you design a microcontroller to interact with the arm. So you control the motors of the arm, and you can sense, the velocities or the forces or the torques the arm is experiencing, and you make the arm do something. For example, in industrial settings, you'd be trying to make the arm grab things and put things back in a reliable manner. Those are things that if I was talking to a room of control theorists, they would be like, yes, of course, these are very obvious applications. Now, what is a sort of not obvious application, a new one, if you will, is using feedback control to think about neuroscience. So for example, we could partition our system into the muscles, which we tend to have a decent model of, so biomechanics and muscular dynamics. And then we say, we sense something about the muscles from our neurons. So muscles themselves have spindles and Golgi tendon organs to sense length and force. And our neurons, I'm being very vague here, right? It could be the neurons in your spinal circuit. It could be the neurons in your brain. Some neurons are coming together to say, given we've sensed this information, what's the best thing to do next? What's the signal which is sent to the muscle to, make our system do what it wants? So these are some examples of the controller and the dynamical system. So I'm going to do some math here. I'm going to talk about state space control. In particular, I'm going to talk about the linear discrete time invariant setting. So actually, Terry gave a model very similar to this. So thanks, Terry. Everyone's a little bit familiar with it now. But basically, we're going to denote our sensing signal y of t, so it's a signal with respect to time, and our actuation u. The controller's job in the linear setting is very easy. You just want to develop a linear causal map, mapping from your sensory input to your actuation output. The system model, there's two parts. The first part is an ordinary difference equation here, because we're using a discrete time setting. Xt is some state that you care about. So if it's an arm, it could be the angular, the angles and the angular velocities of the joints, for example. You have, so the state depends on the current state through the matrix A. And the state also depends on what you do, right? What you do with the motors through the actuation matrix B. There's also a disturbance term here, because even if you had a pretty good model of your robotic arm, maybe your friend comes by and pokes it, right? There's no way for you to have modeled that in advance. So we just let that enter as noise or random variable. And then you sense your system, you sense some transformed version of your system with some sensor noise. So this is the framework that I'm going to be working within for this talk. So I'm going to talk about 3 very common and hopefully simple to understand feedback control techniques, and then I'm going to talk about how people have used them in neuroscience. So the first one that hopefully many of you have heard of is the proportional integral derivative, or PID. This is the control mechanism for tons of things in the real world. And all you have to do is you have to access some error signal. So that could be like, if you're trying to make your arm go to a certain place, you can of course calculate the error between where it is and where you want it to go. And then all you have to do is compute these three sums. So you take a linear combination of your error, of the integral of your error, and the derivative of your error, and then you pick how proportional your control signal is to all of them. This actually works really well for a lot of things. And as the control engineer, your job is just to pick the proportionality constants. There's some rules of thumbs about this, but basically you can just run simulations and tune until you have the desired performance that you want. If for some reason making a derivative or integral term is too hard, that's okay. You can have a PI controller with no derivative or a PD controller with no integral. Okay, so I promised to talk about optimal control. So here is the simplest optimal controller that you can have. And this is called the linear quadratic regulator, LQR for short. So this one assumes that you have access to some state. I'm actually going to go back a few slides to our state space model. So here I'm saying that your sensor is not necessarily directly telling you what X is. But in some applications, because the robot is not, something you can't control, you can just say, well, add some more sensors to sense what we want. Okay, so Y of t is equal to X of t. We know exactly what our state is. So assuming that you have access to the state directly, you pick a cost function that's a quadratic combination of state penalty and input penalty. So roughly, what does this mean? So let's think of xt as, again, maybe trajectory error. So it's the error from where you want to be, and u of t is how hard you need to push the motor to do that, right? So you as the control theorist only have to choose q and r. You actually don't have to do anything else. And you choose that based on your specific application. So maybe you say, I really want to hit this trajectory right away. I don't care how much electrical cost you incur, right? Just put a really, really big input to make you go to the desired trajectory. That would be a very large Q and a very small R. You can do the opposite as well, right? You can say, I'm really, really high on my electricity bills and I need to have a small input. Just make it roughly go along with the trajectory, but make sure your input is not too big. That would be a large R and a small Q. Okay, so you pick that. And once you pick that, you let the people before you who have figured out this problem do the work for you. So you basically solve an algebraic Riccati equation. We don't really need to know what this is. You can call it in a single function in Python or MATLAB. You take A and B, which describe your system. So it's your system model, and Q and R, which are the costs you just picked. And then you get a controller. Now, what's interesting about this case is the optimal controller is actually static. You don't need any memory or dynamics here. You just take the current state and you multiply it by some matrix, and that gives you the optimal input. So it's very nice. Well, it's one of the things we use most. And then I have one more, but actually, are there any questions about this formulation before I go on? Yes.
So you saying the optimal controller is static, but how does this align with the PID, I think, framework that you suggested?
Yeah, so PID, you need a little bit of memory to compute. So you need memory to compute the integral, and you need a little bit of memory to compute the derivative as well. Depending on, usually people will make approximations of the derivative because you can't, technically speaking, you need the future and the past for the derivative, and you don't know the future. So you will need to remember a little bit of the past to find the slope, essentially.
So, but this then is not static.
Yeah, I would say this one is
Completely
has none.
misunderstanding.
Yeah.
So what am I? Sorry, what am I missing?
Sorry?
So what did I miss?
What do you mean? What did you miss? So
Everything.
this one is static, and this one need not be static.
Okay, so that one is not this one.
They are not the same. It's two different methods. Yeah. But what's kind of interesting is this one is, in a sense, much more cruder than the other one. You're just tuning values to try to find what the best behavior is. This one is mathematically proven to be optimal, and the optimal one, in fact, actually does not require. Yeah, I had enough.
I think I had the same question. So these are two completely different methods.
There are two completely different methods.
And the error function is, and you can have it in the analytical form to compute the integral and derivatives, or
What do you mean by the error function?
the error term, sorry.
Cost function.
No, the one before.
Ah, this error term.
Yeah.
Yeah, so you like, let's say you're sensing the current angle and you have a desired angle, you just subtract it off.
Oh, it's not an actual derivative of,
Oh, and then you would try to calculate the derivative of that signal that you're able to sense. So very crudely, you could take the last time steps derivative error signal, right? And you can take the current one and just do a simple slope calculation.
but it's always a numerical like estimate, right?
Yes,
It's
definitely.
never a, like you will never have DE of DT
No,
in a closed form.
no.
Oh, okay.
Yeah.
But in some situation, you might have a sensor which picks up the derivative.
Yeah, that's the other thing. So it depends, right? It depends on how you formulate the signal. Like if you have just position that you care about, then yeah, you will not have a true velocity. But you could just put another velocity sensor on, then you will have the true derivative. But then you will also need the derivative of the velocity. So it's, yeah, some of them will require some approximation.
And then in the second one, it's totally separate, but you just incur a cost on your control signal and the input.
Yeah. You could make the control signal the same thing as the error signal, and then the math is the
That's,
same.
I think that was the.
Thank you. Okay. Yeah, so this is two completely different mechanisms. One is non-optimal and the other is. I'm going to talk about one more, again, different one. It's basically a more advanced version of the linear quadratic regulator. This one is called the linear quadratic Gaussian, LQG. So LQR and LQGR are optimal formulations. This one, the main difference is that it does not assume you directly sense the state. So you sense some linear transform of the state plus some error. And then that makes your controller a tiny bit more complicated. But the cost function is the same as before. You choose the relative importance of the state and the input through Q and R. And instead of solving one algebraic Riccati equation, you solve two algebra. So you call your algebraic Riccati equation function twice instead of once. One of them is actually going to be the same one that you solved for the previous problem. And this time it's going to depend on your system models as before. So A and B, your system dynamics, and C, your sensing function. Q and R, your cost, and then disturbance and noise covariance this time. Because what you're going to use these for is to make an estimator, which is the first line, and then a controller, which is the second line. So since we assume that you don't actually know exactly what the state is, we're going to just try to estimate the state. And the first half of that estimator equation, so the first one there, looks almost exactly like your known state equations. But it's then supplemented with this additional term, because if you model this without this term, you would be extremely susceptible to disturbance and noise, right? So we make a mixture of what we know about the model and make a prediction off of that. And then we supplement that with the sensory information that tells us, oh, maybe a really big disturbance hit you so that your original model, needs another term. And once you make the estimate, you can actually do the same trick as before. You make a static function of the estimated state, and that's your optimal controller. So here, the optimal estimator has some dynamics, but the optimal controller part is completely static. Okay, so now that I've talked about these three types of feedback control techniques, now I can make the connection to neuroscience, specifically sensory motor neuroscience. So the three techniques that I just described are actually three of the very, very commonly used ones when people try to use control theory to describe various aspects of sensory motor neuroscience. So PID, LQR, and LQG, we like them because they're very easy to do. And I think neuroscience perhaps also likes them because they're easiest out of the vast literature of control theory. And they are used to model things that you typically observe through either motion captures or without poking into the animal. So things like the trajectory of your limbs, the torque of your joints, the interaction forces, muscle activations, and so on. Those are the quantities that people that work at this intersection typically measure. The task can vary dramatically. It can be flight. So there's a bat paper in here, I think. It can be flight, it can be walking, it can be reaching, it can be balancing. So the general tool of control theory is not limited to one specific mode of movement or one type of sensory information that you as the experimentalist have. And it's also not limited to organisms. So it could be a human, it could be a bat, a salamander, a fruit fly, a mouse, whatever you happen to have in your lab. Okay. One thing I did want to elaborate a little bit on is that not only can control theory help explain just matching sort of the experimental variables, there's also some general properties that emerge when you try to think about sensory motor control as an optimal control problem. And one of these is the minimal intervention principle. So optimal control functions around the fact that you have a cost that you're trying to optimize. Now, this cost does not need to be extremely high dimension. It doesn't have to be as high dimensional as your state. The cost can be very simple relative to your actual dynamics. So then there's going to be some level of redundancy. There's many ways to achieve the same goal. For example, if I wanted to reach for the microphone, there's many different ways I could do this, or these are very different trajectories, and you still manage to achieve your task. So this is seen in experiments as well, where people will achieve tasks, motor tasks, reliably, but with very much inter-trial variability. And one of the things that optimal control says is that, well, if you encounter a change or a deviation in a dimension that's not relevant to your task, that's fine. You don't have to do anything about it. And that will help you conserve energy, right? You don't have to act on things. So let's say I'm trying to reach for this mic and someone comes and pushes my hand this way. I don't have to come back to where I was before. Maybe I had a plan implicitly or explicitly of reaching like this. Someone pokes my arm that way, that's fine, I can just do this, right? So you can allow variability to accumulate in dimensions that are not relevant to your task. And this is something that I think is philosophically kind of related to low dimensions in manifolds. And here it's arriving from the fact that your cost is low dimensional, but your system is high dimensional. And so you get a lot of redundancy in how you can achieve the task. Okay. So there are some benefits and downsides as with all modeling techniques. So the benefits, one of the first benefits of control theory is that it's really easy to interpret. And in a sense, it is a sort of prior model. So depending on the way you're doing things, you're either not fitting data or you're fitting data to like 1 or 2 parameters. So it's very easy to tell what the system is doing. In the case of optimal control, you know that it's achieving this cost. And you have all the analytic guarantees that come with that. Being a theory that came from engineering, so it's not applied to any specific part of sensory motor system, we can apply it across a number of different scales. So you can apply it to spinal circuits, which is just 3 or 4 neurons through your spine. You can apply it to maybe one part of the sensory motor neural system that you're into. So for example, motor cortex. Or you can say, I actually want to model the entire system from sensory to motor through the spinal cord, all the muscles. That's fine. The framework allows you to put those into your controller design problem. And so it kind of lets you put many aspects of sensory motor control together, which is nice from a theory perspective, because for experimentalists, there's good reasons that you might want to focus on one modality or one animal or one area of the brain. But the theory can say you can put together these different findings from these different kind of parts along the sensory motor pathway. So, sensory processing, motor control, biomechanics, neural computation, these are all features that you could put into your model. The challenges, one of the main challenges I've encountered is that it is interdisciplinary, and control theory is not perhaps the most popular branch of mathematics around. So often you find yourself having to explain control theory, which is why these 3 very simple controllers are the main bedrock of the current models, because these are the simplest ones. Or you find yourself in the opposite case of trying to explain neuroscience to control theorists, which has been surprisingly challenging in some situations as well. There's another problem that's a little bit more philosophical, and that is, so control theory says there's a system and there's a controller. But in neuroscience, what is the system and what is the controller? Because from engineering, someone builds a system and gives it to you, and you control it. But if we're just trying to model neuroscience, the whole thing is given to you, and you're not actually controlling any of it, right? You're just hypothesizing that it's a goal of the system. So here's some examples of ways we could partition sensory motor neuroscience into controller and system. So the first one I mentioned already, muscles and neurons. You could pick as your system something not related to the body. So motor cortex, for example, is known to be highly dynamical. People will use ordinary differential equations like x equals ax plus bu to actually model motor cortex. And in there, the inputs are kind of just the other neurons that we know connect to motor cortex. you can even zoom out more and talk about brain as controller and body as plant. That's the thing that I think most people will think of right away. But you can zoom out even more and say the whole animal is the controller, and you're governing how you interact with your environment, right? You see a prey and you want to go and eat it, right? You see a predator and you need to run away from it. All of these can be correct depending on the setting you're in. So one sort of philosophy that I like is to model what you know as a system. Now, in neuroscience, I feel like many things are not known perhaps as concretely as engineers would like. But there are things that you'll know more things about and things that you'll know less about. So put the things that you know or have relative confidence in into the system box. Okay, that's going to be the dynamical system you're trying to control. And let the other things that you don't know what they're doing be the controller. So, and we're going to assume, this framework assumes that the overall system is able to achieve some kind of task, right? So we know that overall, us as an animal, we're very good at executing various sensory functions. How does all the neurons in our body do that? We're not quite sure, but we know that the whole system is able to do this. And then so optimal control assumes that through evolution, your controller and system evolved to achieve this goal. So in particular, your controller evolved to help you achieve this goal. And you're going to try to find more about your unknowns by kind of letting it perform this optimization for you. Okay, so exactly how do I make a model out of control theory? So we can have a dynamical system, you have a model of it, you might have some objectives and you might have some constraints. These can be related to the experiment that you're trying to match it up to. Then you can use your controller design. So you can use PID or LQR or LQG, one of the methods I found, or you can use more complex methods. It's fine. Your favorite controller design method will give you a controller. And then because you have a reasonable model of your system, hopefully, you can then simulate your controller with your system model, and that will produce predictions of what quantity. So for example, if your dynamical system model is your arm, and you're trying to model like your neural control of your arm, you can make your controller, that'll be like what the neurons are doing. You put that together with your arm model, you can make simulations of how the arm is going to move in the end. Okay, and then you can compare this to whatever experiment you design. So in this case, you maybe compare it with an actual arm movement. Now, if your system model is pretty good and your objectives and constraints are reasonable, then you can expect a reasonable amount of match between these two. But if you want like true, nice numerical matches, typically you will need to do a little bit of parameter tuning. For example, in the linear quadratic regulator, I said that you get to pick the costs, right? Now, when we do a reaching task, what is the exact proportion that we care about reaching versus energy? Well, we don't really know, right? Like we can say maybe, energy is about as important, but is it exactly equal? Is it, 10% off? So those are some free variables, sort of, that you could then try to fit the experimental outcomes to. Yes.
So like in the case of reaching, I guess there's like one control for just moving your arm around. But if you have to both move your legs to get close to something and then reach something, does that mean that there's two separate controllers? Or does your controller just become like more complicated?
So this is a good question. So in terms of multi-limb coordination, so you can, so there's like spinal circuits, right? And those are very fast and quite localized. And then there's the more advanced kind of brain circuits that allow you to coordinate complex movements, right? So the answer I think there is that if you want to be modeling the whole neural system, then you'll have many different kind of levels or layers actually of controllers working from fast and localized to slightly slower and more centralized. So you might there have local spinal controllers for your limbs separately, and you might also then have coordination through one more controller that sits on top of the other controllers.
Is that the way engineers do it?
So there's a lot of examples where engineers will kind of hack together this sort of layered framework.
What do you mean hack?
So, well, I guess you could also say biology hacks together. So what I mean is that people will just say, oh, well, we choose the size of, the local lower ones rather arbitrarily, I would say. And then we choose how they're hooked up together also rather arbitrarily. And we also choose the control laws, this is great, rather arbitrarily, because there's a lot of tuning involved. Now, if you wanted to be smarter about the whole thing, you would put the whole thing together and try to design that all at once. But that's actually mathematically a little bit more complicated. So usually we'll just fix some elements and progressively design the other ones. Okay. Other questions? Yes.
So, but here you have to have some kind of strong normative assumption about what the cost has to be for the person doing the thing, right?
Yes, exactly. So yeah, you're assuming that there is a cost, first of all. And I think experimental, like some experiments have shown that we do behave as if there is a cost. But yes, one of the main assumptions of using optimal control is that indeed we ourselves are optimizing either consciously or unconsciously for something.
But what if you had a variable that's like, instead of metabolics, but I'm lazy. You have to encode this into something that's actually then controllable. And then there's some stuff that you don't know, does that actually matter or?
So I think I'm lazy actually falls pretty well into LQR.
Yeah.
You just make the R large. Yeah.
Right.
If you have, I should have explained it like that. But if you have something else that you're not accounting for, so it depends. So when you're doing optimization, not every part of your objective and not every constraint will necessarily make a change to the controller structure or the numbers per se. So you kind of just have to find what I would say are like the strong objectives and the strong constraints, and that'll help you figure out the problem. Yeah. Okay. So here I put the arrow between the simulation and the experiment because that's what people usually do, right? You're measuring outputs and you're comparing outputs. You're not actually poking into the brains of your subjects, but perhaps we want to poke into the brains of the subjects. So then we want to say, on the outside, we are behaving as if we are an optimal controller in some sense. Can we use that knowledge to look at the inside? So maybe the inside of an organism, the neural connections and dynamics and so on, are somehow related to the inside of a controller. So that's the area that I've been sort of looking into. And the specific feature that I'm going to talk about for the rest of the time is what I'm going to call internal feedback. And this is based on work during my PhD and also with Terry. So here we have, I've chosen the dichotomy of animal and environment. So the bottom, the black circle, that's what I'm going to call external feedback loop. And so you have some environmental dynamics, that's the bottom. And then you sense something about the environment. You use some computation. You might have to communicate the information throughout your body. And then you choose an appropriate actuation. So this is actually what we normally just call feedback. But in this case, I'm making the distinction between this feedback that is external, right? It's you and the external environment, and the inside of the animal, where there's actually a lot of information flow in the opposite direction, from actuation back towards sensing. And it's not immediately clear how that's helpful to our nice feedback loop. So the place where this is perhaps most well documented is in the visual system, where you have your environment, you sense it through the eye projects to thalamus projects to cortex, and then cortex putatively takes you from kind of a retinotopic pixel representation to a more semantic representation, right? So I go from a blob of black pixels to microphone, essentially. Now that directionality, I think intuitively makes sense to everyone. If you do computer vision, that's your CNN basically, right? Your CNN is transforming you from pixels to representation or classification. But then actually in the brain, there's plenty of feedback in the other direction. And this happens across I think almost all the sensory modalities. So for somatosensation, it's the same. You have the forward path, and then you have very strong recurrent or feedback connection. And there's a variety of reasons that people have hypothesized why these are there. But as a control theorist, you look at this diagram, and the way I've drawn it, you can also see it's missing basically half of it, right? We spend a lot of metabolic energy on vision, humans specifically, but we better be using that to make ourselves better at surviving in the world, right? You don't want to spend a bunch of energy on a sense that you're not going to do anything with. You need to act on the world. So here's the same diagram with a little bit more. So we have added motor areas and spinal cord. And then when you add that, you notice that the feedback is not just between visual areas, but also between motor and visual areas as well. And the main idea there is efference copy. So you send a copy of your motor output to your vision or other sensory areas, because you can use that to predict what you're going to sense. So yeah, sensory processing takes a lot of energy. You want to basically get rid of the predictable elements as fast as you can. If I decide to move my hand in front of my eye, I don't want my visual system to be surprised by the, oh, there's a new moving stimulus that I have to be attentive. It's just my hand, right? I knew I was going to do that. Okay. So we decided to try to look at this in the framework of control theory. So internal feedback, again, information flow from actuation towards sensors. We're going to try to look for it in controllers. So here's PID, and here's LQR. We're off to a great start. There's no internal feedback in any of these. There's a bit of dynamics in PID, but for LQR, which is a purely static controller, you take your sensory information, you multiply it by a matrix, and then you are done. Okay. We have one more, LQG, and this one, because of the prediction, it actually looks pretty nice, and it has 3 paths of internal feedback. So what I've done is I've taken the equation on the right, which is the standard way of doing optimal control in the linear quadratic Gaussian setting, and I've just literally translated them into this block diagram. So here I have the 3 blue lines. Let's go through the top one. So that's the one through B. So that's the one saying, depending on the course of action I've chosen, how will the state evolve based on what I'm going to do? That's basically efference copy. Okay, that's nice. The second line, the state model prediction, that one's the one that depends only on X. So you're saying, if I didn't do anything, based on what I know about the external world, what's going to happen next? So you have a model of the world kind of with you and without you in this model. And finally, the last line, there's sensing model prediction through C. That's saying, well, the states are not exactly what you sense. So you just need to transform it back out to sensory information. So if you're predicting that you're going to see a hand, you don't literally see a hand, you see a pixel that is in the shape of a hand, right? So you just need to transform that back out. Okay. So here, internal feedback is basically, it's serving the estimator. And this is good. So then we're saying, okay, we have a structure in our controller. Let's try to map it onto what we know about humans or biology in general. And this is something I've been thinking about for a while, and I've thought about many ways this is problematic, but I'm going to talk about 2. Okay, so one problem is that implementation is not unique, and neither is the circuit or the dimension. I'll give you examples. And 2 is the presence of sensory motor delay. Okay, so let's start with the implementation. So this, people have worked with this a little bit in sensory motor neuroscience, and we kind of love it because all of the signals are very interpretable. The models are very interpretable. We just have to go into the brain now and look for these things, right? We even already have the efference copy idea. Let's just go and look for signals that correlate with that. So we assume that part of the brain, maybe cerebellum, maybe cortex, is doing these various functions. But any first-year control student will tell you that you could do this with any arbitrary matrices and get the exact same performance. And I don't mean that it's approximately the same. I mean that mathematically it's the same. If you only had access to Y and U, these two, you cannot tell the difference. And you could have basically arbitrary matrices. There's some constraints on the spectral profile of the matrices, but there's enough freedom that you can really make whatever matrix you want. And that kind of takes away all the nice interpretations of all the signals that we have. Okay, and then at this point, you might, to salvage the situation, say, but we know that there's going to be, maybe 3 types of feedback and 1 type of feed forward. And no, that's not the case either, because you could equivalently implement this with this diagram, again, with an infinite possibility of matrices, and it's going to look the same. So neither the quantities nor the structure have to look the same. The only real conserved feature we can really talk about is that if you have to do estimation, then you have to do it either through feedback or through dynamics. And of course, the brain does need to do estimation and prediction, so that works out. But exactly how it's doing it structurally, it's not very clear based on the math that we have about implementation of controllers. The second problem that I identified was that of sensory motor delay. So weak control theorists have gotten a little bit, I don't want to say spoiled kind of, because the systems we're working with compute on fast metal and transistors, and we don't have that many delays. And even when we do, we're able to make assumptions about them that basically amount to they are small. And so we don't really have to think about this type of thing. But animals, on the other hand, every time you send information somewhere else, you have to do so with some amount of delay. And I've chosen to focus on delay, but that's obviously not the only issue. Right? There's going to be noise problems, there's going to be encoding problems. Delay doesn't even have to be literal conduction delay, because it could be if you're using rate coding, for example, you need a little bit of time to change your rate, right? You can't fire infinitely. So delay arises. Here's a nice diagram from this 2018 paper that kind of maps out some causes of delay through a spinal stretch circuit of an animal. And this only gets worse if you want to involve the brain in any of your computations. And right, so you would have to travel from the spine to the brain, but there's distance there. And then even if you exit it immediately from the brain, having computed instantaneously, there's still going to be a delay coming back down. So there's plenty of places where that might be interesting to consider. So then we decided to say, okay, let's go back actually to our very boring LQR model, which, let me see if I have it close by. Oh, here we go. Here's the LQR model on the bottom, right? There's not much to look at there. But we're going to say, let's take that very simple model and add a little bit of delay. Okay. So we're going to have the exact same thing, and we're going to add one more block that we're going to call motor delay. It's actually just the delay, right? It doesn't have to be motor. I could have put it earlier and called it sensory delay. So now we have our controller, and our controller, which is K, maps the sensory information X to X1 in this case, to some output. But once you've decided the output, you still have to conduct it, or send it to the muscle, and the muscle is going to have its own delays. There's going to be some motor delays, and then you're going to finally get to send your sensory signal, your output signal to your muscle. Okay, so this formulation is a little bit strange, but we've chosen the variables in such a way that you can basically stack the two x's into one vector, and then it becomes a slightly bigger LQR problem again. So we didn't want to do any new fundamental math. We just wanted to design the variables cleverly so we can just make another LQR problem. That is what we did. And then you can use LQR to figure out what the optimal control is. Now, as it's currently written, what you would need to do is actually have a small feedback from the motor delay back towards your sensory output. And that'll let you be optimal with that delay. So then we did a simulation. And so this one says sensor delay, but actually in control theory, there's a nice thing where things that have to do with actuators and things that have to do with sensors are mathematically dual. What that means practically is you just transpose a couple of matrices and everything else comes out the same. So numerically, it will be identical whether you do this for motor or sensor. So on the bottom, the first line, the ideal no delays line, is its original LQR. So if you didn't have to deal with delay, you can do a lot of tasks really well. The task difficulty here is essentially the stability of your system. So task difficulty is less than 1 means that even if you did nothing, eventually your system will behave the way you want. So this might be like if you're asking someone to track something that's right under them. You can do nothing and just let your hand fall and it'll be good. Task difficulty at 1 means that your error is going to stay the same if you don't do anything. And task difficulty above 1 means if you don't do anything, you're going to have a larger and larger error and you're going to diverge to infinity. We don't diverge to infinity, but we get far enough away and it's just as bad. Okay. With internal delay, with internal feedback, so that's the picture on the left here, we don't do as well as no delay, which is reasonable, but it's decent actually, especially for task difficulty less than 1. Then you might say, okay, but your formulation basically has internal feedback baked into it. That doesn't seem fair. Okay, fine, let's get rid of K2 and redesign that optimally. That one takes a little bit more math. But basically, if you don't allow that path through K2 to exist, then you have pretty bad behavior, especially as you pass difficulty equals to 1, you have this sort of exponential growth. Actually, this is already a log causes of exponential growth. And when you get to high enough task difficulty, there's a dotted line because you can't actually make a controller that even stabilizes for you. No matter what you do, your task, you will do the opposite of achieving your task, you will diverge. Okay. Well, you might, so I mean, a discrete time system, so you might be sampling in a way that your delay is not just 1 unit of time, right? Delay is probably several units of time. So let's have two delays, just as a general concept. You can use the exact same machinery and design a controller. And at this point, I think some of you might recognize that something is wrong with this picture, but I'm not sure if anyone wants to say what's wrong with this picture. Okay, so we're not in an imaginary control world. We're trying to map this onto, the body, for example. And motor delays in the body arise from specific biophysical features, right? One of these is conduction delay. One of the things we said is we can, it takes a while to conduct from your brain to your leg muscle, let's say. So that's why we're putting these motor delays there. It takes time to conduct between those two places. But then if you look at the line through K3, that one's instantaneous, that one's not delayed. That one's saying you can just immediately conduct between these two places. Well, if you had a neuron like that, why would you be doing this, right? You just put that one in the forward and be done with it, not do any of these dynamics. So that's not very good. But we can fix the implementation a little bit. We just shift all of that before the two delays, and mathematically it's going to be equivalent. So essentially what you're doing is you're making a copy of things downstream from you, and you're using that to help you predict. So essentially it's a predictor. It's not explicitly a predictor, but it's implicitly a predictor. Okay, so coming back to internal feedback, then we can say, okay, internal feedback helps you predict. It carries some, information about the downstream delay dynamics. This is a nice circuit. Is it the only circuit? No, of course not. There's many other circuits we can make that are mathematically identical. And at this point, the question that I'm going to ask that I don't have an answer to is, which is the best one and which is the real one if the brain is doing any of these ones? The main conserved feature we can say is, again, with motor delays and also with sensor delays, as before, the controller needs either internal feedback or internal dynamics locally to compensate. But as to which one is the best and which one is the real, this depends on the specific circuit you're considering and kind of the types of wiring costs you might consider. So as an engineer, I might just say the left one is better because it looks simpler, right? But depending on what you hypothesize our neurons are capable of doing, it could be that in neurons, the right one is easier to compute, right? So I've drawn it in terms of like matrix multiplications and signals, but certainly there's internal dynamics and computations in a single neuron. So we don't know. But we decided to just put everything that we talked about together. So this is the LQG controller. So that's the one with output feedback, where you have a sensor that doesn't directly tell you what you want to know. And so we have the 3 blue lines. Those are from the original model that I talked about, the 3 nice estimating quantities. And then we also added in the sensor delay and the motor delay. So mathematically, this is actually valid. So the nice thing that we found is when you do both estimation and sensor and motor delay, if you massage the equations a little bit, you can draw them in a way that's completely separate. So every estimation and every different delay contributes a distinct source. And they're all doing prediction and compensation. So this is something that we put out in PNAS recently. But of course, there's the additional problems that I talked about, right? This is completely non-unique. The other thing is that it doesn't include internal communication delays. So I've been talking about things kind of in an assumption that your pathway is kind of like one pathway, and there's delay along it in various places, and you might have to estimate. But actually, the brain is highly distributed, right? You're not necessarily having one pathway where everything is together. And to illustrate that, we just have a very, very simple second model. So what's another type of internal delay that we can have? Well, let's say we have 2 different subsystems. So we can say perhaps these are our 2 arms, left and right arm. Your left and right arm physically are coupled through your torso, but depending on the task and the context, you don't really experience that. So other than the fact that I can't make my right arm float off, very far away from my left arm, dynamically speaking, they are quite distinct. But for example, if I was trying to like walk on my hands or something, then they would become extremely coupled. So there's some degree of dynamical coupling between them. They have local controllers. So this goes back to someone's question earlier about spinal cords versus brain, right? The different levels of complexity. So here we can say you have some local spinal controllers for each one of these, but you might also have some coordination between them, through the brain or something like that. But any additional coordination that you'll have, it's going to require more communication, and therefore it's going to incur delay. So we simulated this system, again, with task difficulties. So this x-axis is different because the task difficulty here starts already on the very left. We're starting with difficult tasks. Because remember, 1 is the threshold where below 1 means if you don't do anything, you'll eventually reach your goal, and above 1 means if you don't do anything, you will diverge. So this is if you don't do anything, you will diverge. And again, the bottom line is if we didn't have delays. So the bottom line represents if your circuits that control your arms were able to communicate to each other with no delay at all. So instantaneous optimal computation. Obviously, that's the best. And obviously, we don't have that. The second best case in pink is if we allow a structure like this, where we say, within a local region, the delays are negligible. They're so small, it doesn't matter. But if you want more centralized coordination, you will have to do it with delays. And then, it's worse than not having delays, but it's better than not allowing coordination at all in most cases. Now, what I found interesting about this plot compared to the other ones is that even for task difficulty greater than 1 here, actually the blue line and the pink line are relatively close together. So there's a regime for which you don't need communication between your controllers necessarily. And this, I think, is sort of interesting link to motor cortex ideas. So motor cortex putatively is formulated like as a homunculus, as a little person. So you have a little part of your motor cortex that's your hand, you have a little part that's your leg, your trunk and your other leg, and so on. And that's sort of like these local controller signals. But then there's also a ton of studies that say not quite the opposite, but something like the motor cortex also has whole body signals throughout these putatively homuncular areas. So it kind of sounds like you're saying opposite things. Well, which is it? And what this model says is that it depends on your task and how functionally coupled these two systems are. If they're not very coupled, homunculus representation is fine. Your left arm doesn't have to know about your right arm. But if they're very coupled, then yes, you will need whole body signals. For example, if you're trying to do like downward dog in yoga, you need all 4 of your limbs to coordinate, right? And in that case, you might want to have whole body signals instead of just purely separated homuncular representation. Now, this is a very simple example, but to do this at scale, to think about many neurons, for example, or distributed control, where basically you have a lot of different streams of input and they communicate to each other sparsely or not at all, you need distributed control. And that basically leads to structured optimization. So optimization problems that have structure or sparsity. So that's actually kind of the main area of control that I worked on, but the math is a lot. So I've decided to just stay with this simple example for today. Okay, so just to sum up, right? If you take away nothing else from this talk, I still want you to take away the idea of control theory, which is that if you're given a system that has a model through ODEs, how do we make it do what we want? Now, many of you will actually know how to solve that for a specific, smaller problem that you're used to doing. But if you encounter a more difficult problem, there's a whole branch of math, control theory, that will help you design your controller. And simple controllers, right, PID, LQR, LQG, can explain some behaviors. That's in the literature. But how that relates to implementation is not yet clear. And there might be something to think about there in terms of manifolds, in terms of just the complexity map between what's on the outside and what's on the inside, so to speak. And one thing that I'm interested in working on is, for the future, to characterize the space of implementations. So I showed a lot of equivalent circuits, right? And those are not exhaustive at all. And I'm interested in characterizing, if I have some kind of delay or other types of neural constraints, what are all the possible mathematical equivalent implementations? It's interesting to me from a math perspective, but also I think it will allow us to provide essentially a parameterized space that we can then try to match to data. So yeah, that's the end of the talk. Thank you all for listening.
I'm wondering if the delay is equivalent to timescale. What means the internal feedback for me is like a nested controller system. As you mentioned, the neural muscle can run quickly, the different copy go back slower, then the environment goes even slower. So they may run in different clock.
Yeah.
So is this two equivalent? You have delay, then you have different clock.
Yeah, so that's definitely, so that's like one other direction that we could look at is separating controllers along these different types of timescales. If you wanted to put them all together, you could probably, yeah, massage your equation a little bit and put together a controller with different delay scales that communicate to each other. And you can ask like, what's the optimal configuration, for example, of the combination of these scales? That is most likely to be not at all convex. So we for now try to break it out into like one time scale at a time and think about what we can say about one time scale. Does that?
Yeah. Complexity definitely. If you have different time scale, would be more complex, but the system will be more powerful. Like the motor neuron and the muscle can constantly update in very fine time scale.
Yeah, that's true. But I mean, there's still a minimal kind of delay there, so you won't have a super fast time scale. The other thing is it depends on the task. Some tasks have very slow time scale, so you can get away with a lot of delay, and some tasks have time scale so fast that actually you need to make basically kind of like muscular or subconscious adaptations to fit those tasks, like batting a baseball or like pitching, for example.
Yeah, the other question is in the system, can you define a boundary of this system can tolerate to the delay? Because if you play a video game, the lag is too long, you can never adapt it. And if the lag to be negative as well, is there true boundary?
So the way that you would make lag negative, if I'm understanding correctly, is if you would just try to do that through a very good prediction of the future. You will not actually see the future, right? Yeah, but certainly in some cases, you will not be able to deal with larger delays.
So is this like a transition? Below the delay is always the.
Oh, I see. It's dependent on the system dynamics. So like the like this type of thing that I showed, you can make a 3D one with delay in the other axis as well. And it's going to be something like that. Like for a combination of delay and task difficulty, you will need a maximum delay that you can tolerate. Yeah.
So I'm not a control theory expert, but just imagine, there are nested feedback loops for the control or spinal reflex, and some feedback is directly from the early sensory areas, some are more higher cognitive feedback. I mean, obviously the delays are different depending on the loop, right? I mean, I just imagine that the control done by long delay loop is an easy problem because the quicker part is already subtracted and under control by the reflex part. So it's, I mean, sort of the slow area that has to deal with is an easy problem with a lower task difficulty already.
Yes, exactly. Yeah, that's right. So yeah, based on the conduction delays that we're saddled with as organisms, it's beneficial for you to act really, really fast. So that's what the spinal circuits are doing. But within one neuron, you can argue kind of how precise you can be, and you don't want to be acting with so much imprecision that you somehow make the problem worse or be like sensitive to some types. So there's also the question of like how much you should get that spinal circuit to do compared to how much you will allow the, let's say, conscious or somewhere in between there, how you will allow that to intervene.
Is there a systematic way to sort of hierarchically design?
We seek a systematic way to hierarchically design, as I think Terry might have asked earlier. Yeah, how do we do this in engineering? It's all ad hoc, right? We just fix something and then we design on top of that. Yeah.
So I just could interject that there's another PNAS paper about a year before Lisa's, which was about mountain biking. So, and John actually created a game that you could play, which is as if you had first of all, it would shake you because that was happens, you go down a hill, you get, your bike goes up and down and so forth, and presumably all the reflexes, the spinal cord are taken, without your thinking, stabilizing you so you don't fall over. But then, okay, so that's the first layer on the model. And you actually had an example of several different layers with different time delays. But okay, but if you're coming down the mountain and you see a turn and you have warning, that you're going to hit that in a couple of seconds, you can now that's the cortex now because you have to see things. But that allows you to set up all your lower controllers to prepare for the turn, right? So there's these layers.
That one, it was just additive, actually. So
It was actually, we did the experiments, John did actually, and if you do the analysis, you can put time delays not into the brain, but you can put it into the steering wheel, right? In terms of two things, bits of information that you can transmit from the steering wheel, which is sensory limitations, but also the time delay between turning your wheel and the actual turning of the cursor on the screen. And interestingly, those two different ways of perturbing the system were additive, which was apparently it doesn't have to happen, right? It's telling something about how, in fact, this is a related question, which is you're doing this all from first principles, and then you deliver a set of equations, you deliver a controller. How do you learn all of that? The brain has to learn that stuff. It doesn't, the engineer in the sky doesn't give you all of those gains and things ahead of time. You have to learn them. And so how do you incorporate that into your framework?
So actually I've always thought about it as like the next logical step. If we know how it's implemented, then we have a guess as to how it's learned. But the implementation, so when I was showing all these different wires, like which one is better, right? So you probably also want to think about which one of those would be a better architecture to learn upon. But learning doesn't have to take place quite as fast, right? So you have some leeway there in terms of like modulating from higher areas, essentially. Yeah, so that's.
So we actually have some hints from neuroscience, which is that motor learning, a lot of that is taking place in the basal ganglia, right? So your models have been mainly cortical with time delays in the motor cortex and the visual cortex and so forth. But one of the things we know about the basal ganglia is that what it does is it allows you to do a sequence of actions to achieve a goal. And if you're in sports, that means, learning how to play tennis with all the different ways of hitting, forehand, backhand, on your feet, running, so forth. And you learn, actually, the basal ganglia of the dopamine system is there, reward prediction error to help you learn to play better tennis, but it takes a lot of practice. You have to practice, right? And so, but there's a loop between the basal ganglia and the cortex. So that's yet another kind of controller that you have to put in. Much slower time scale, by the way, that as you say, for learning.
Yeah. So actually, I mean, I think it's interesting that, like, I like to say cortex, I guess, because that was the first part of neuroscience I absorbed through osmosis. But none of the things I'm saying actually need to be cortex per se, right? It's just a loop with a delay. So.
Oh yeah, no, that's true. But our model was about the cortex. but here's what's interesting is that one of the things that cortex really has in abundance is memory, huge memory systems. And if you do distributed control, as you know, she's one of the world's leading experts. Lisa, we're learning on distributed control. You have multiple controller. She solved that problem, right? That's a major problem. Is that you need more memory? Each of the controllers.
So I've been thinking about that one. There's a reason that I didn't talk about that one here, is because I ran into the same problem that I ran into here, whereas the nominal one, the one that translates directly from math, that one has a lot of memory. but you could implement it in a way that doesn't need as
Oh,
much. heat.
really?
Yeah.
Well, John didn't tell me about that.
I'm not sure if John has thought about this.
He's a nobody.
Yeah, so that's why, so like, yeah, in the beginning, I was very like, so like, if you talked to me like 5 months ago, I would have been like, yes, these implementations match what we know, but now I'm kind of saying the opposite, which is these implementations are not unique at all. We need to find some way to characterize them before we make any comparisons.
You don't need a unique solution.
You don't need a unique solution, but you want the solution to have some type of structure. Otherwise, what's the point of having a prior model at all? You just throw a neural net at it, right?
Yeah, along those lines, what feature of the brain would you look to provide the most powerful constraint of this, multiple equivalent circuits or control?
So currently, I think it's the way communication is done. And I'm not sure if it's the most powerful constraint, but I would say it's the point where standard control theory most diverges from the brain. Because as I was mentioning, transistors and neurons, different, right? So that's an area that I feel like the current theory is really sort of inadequate. So that's why I'm trying to add those. And I do think it will be a major constraint, because what pops out of these models also is that if you didn't have the constraint, the model would look super simple. But you add this one constraint and suddenly you have all of this dynamic estimation things, right? So if you want to look at implementation, the constraints of implementations are critical to how you would look at that. So yeah.
You mean the conduction delays?
Yeah, so conduction delay is one. I'm also thinking about because conduction delay plus like electromechanical delay, for example, that's really kind of a double whammy for you. So yeah, so not just conduction delay, but time is very important.
So one of the constraints in neuroscience is that there's a very high cost if you want to be fast. That means you have to have a very big axon, high diameter, but very slow bit rate. So one of the constraints is that you're not dealing with wires that have speed of light and high bit rate. But it turns out, and this is again the first paper 2 years ago, if you have a diversity of fibers with different diameters, with different bit rates, the smaller ones, you can have more of them in that same volume. Those can carry many more bits, but they're very, very slow. But if you have an array of diversity, and all the nerves have huge diversity, then the control system behaves as if it's both fast and accurate, even though no single axon is fast and accurate. So this is another constraint from nature, is that you can take the constraint from nature, figure out how to create a control system around it that solves the problem so that John calls it a virtual. We have a virtual body that seems to be able to do things fast and accurate with components. No single component is fast and accurate.
So in all of this, it sort of seems like we're talking about a scalar objective all along the way. And I at least in ecology, the applications, there's always a multi-objective problem. And I wonder, do we not worry about that here because the timescales are just so short, or?
No. So it's for simplicity that I'm making scalar systems, but everything you do here can be generalized to vectors essentially, yeah. So your multi-objective can come in through like Q as so your X's are, I don't know, your species maybe, and you care about like the different species being alive.
You want like both. For example, you want to have the ratio of the two species to be within bounds, right? So this is like if you.
So that would be like a cross term sort of, between the two species. Yeah, you can definitely formulate that.
Okay, so I know how it works for ecology, but I'm curious about why we don't care about it here, or why we didn't. Like, is there a scalarization thing that just sort of comes?
Oh, no. So I'm just making a scalar example because it's easier to talk about, but everything I talked about can be applied to vector systems.
Okay.
So there's nothing stopping you from doing that. Yeah.
So just a general question. When does the internal feedback is able to modify the action online? Like you almost always have an internal feedback. So if you're reaching to something and this changes while it is moving, sometimes you change your action, but sometimes you don't change your action, but you still have the internal feedback. So is it relayed like into different circuits, or it has to fall in a certain time when the motor function is being executed? Like what is the relationship when you have an internal feedback, but sometimes it can induce a change of action, but some other time it doesn't?
So the internal feedback in our models are usually just predicting what's going to happen because you will act with delay. Whether you change your course of action, so if you experience like a big disturbance, then that will come in through your sensors and you'll decide. So the internal feedback itself is not going to decide whether you change your course of action or not. That is encoded more in the objective. So basically, when you design your controller with the objective, whether or not you have internal feedback, that controller is going to decide if someone pokes you away, whether you need to come back or you just take a different path. So that will automatically be taken care of by the optimization formulation. Yeah, regardless of the implementation, actually.
I have sort of a long-running argument with a colleague about the how accurate the system model needs to be in order to achieve a reasonable goal. And so I wonder if you could comment on that here.
So I think, okay, so actually there's a short and a long answer. So the short answer is that the whole reason for feedback control as opposed to open loop control, part of it is that it does introduce some intrinsic robustness to system models, essentially. The more advanced answer is that there is a specific branch of control theory that deals with robust control, essentially, and that's the question of if my system models are bad, and there's mathematically precise ways of quantifying just how bad, right? And the easiest one is to say like you're within an epsilon ball of your nominal one, but that's sort of boring in a way. You can structure it much more. So I don't know if you were the person I was talking to. So like if you had a power grid, for instance, and you were like, my line models are not that good. You're not within an epsilon ball, right? Because lines that don't exist. That one's not going to be wrong. So you can structure your error. And then there's all kinds of math. So basically that's actually my advisor was the main robust control person, where you then try to say like, I can still guarantee the objective within a certain range if I have these certain characteristics on my model uncertainty.
You just have to have the fishing within that range. Not that is the control that you want, but that's basically right. But then you have the multiple inputs here. You have the natural inputs and the fishing inputs going to have to be a sum of that the control input will be that. I was like, do something with it. Oh. Any other questions? So I have a question. Somebody else? Oh, Tanya, yeah.
So on the question of distinguishing different implementation, so some of them will be more robust, the other one will be less robust, and different implementation, you showed multiple matrices. If it is implemented in reality, each connection has some noise associated with it. So can I distinguish based on robustness and perturbation different?
Yeah, that's actually a really good point. So yes, that is something that I should look into. Yeah. So usually, the thing that I described, which is like being robust to variations in certain places, control theorists basically don't have to look at that for implementation because your implementation is code on a microcontroller. There's not going to be, right? So I think that would be actually really good to look into for comparing against different implementations. Thank you.
Yeah, I have a question. Like, so, I mean, in some natural systems, like people have found that, for example, this, taking advantage of basically the feedback that occurred in the system. If you actually give it sort of like the wrong kind of schedule, you can actually get a resonance amplification catastrophe kind of thing. And it's basically, and you don't know what time, because for example, the stiffness of the system, the natural resonant frequency of the thing will be different depending on the change in conditions. Is there a general way to avoid such a kind of thing?
So there is actually a different, that problem, I think, if you're saying that the time constant is uncertain.
Yeah, so basically like, for example, some unusual time constants will just get the feedback will be completely wrong and just because it gets a runaway system kind of thing. But you cannot naturally predict. I mean, evolution is selected for this not to happen. But in some cases, you can actually find sort of frequencies of stimulation that are outside of natural occurrence that actually leads to the system to have such a property.
So actually that question is more well studied, the question of like uncertain smaller delays. So some people have worked on that because there's direct analogs of that in like networked control. Yeah, and there's ways of guaranteeing that. But the other thing I would maybe ask is if you're simulating it in a range beyond what's biologically feasible, I mean, your system has never had a chance to encounter that. So is that relevant to the?
Oh, actually, people have done it. That's the reason there was a science paper a few years ago that we basically getting osmotic, osmotic shock, which is basically like basically high molecule density, like, and then alternating, I think that was every 8 minutes, would read the cell to die because it would just basically some of the responses would just go and run away kind of thing. But anyway, okay. What else? Okay, well, let's thank Lisa. So I guess since we ran over potentially, we just have to, we can just take a, we can just, hang out until lunch, just like, because it doesn't make sense how to have a break and discussion, so you can.
Well, wasn't there supposed to be a discussion?
Yeah, so we'll do this, we'll move the discussion to afternoon discussion. So instead of having like 2 discussions. And we can, your lunch break instead of being hour 45 minutes will be, 2 hours and 50.
I thought you were going to say we're having the discussion now.